Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our special SETI Live. My name is Franck Marchis. I'm a researcher at the SETI Institute, Chief Science Officer at Unistellar, and CEO of SkyMapper. And today, we are going to talk about something very interesting. Everybody's waiting for this SETI Live. We are going to talk about the exocomet or interstellar comet 3I, that's the way we're going to call it. And for this, I invited my colleagues, Ariel Graykowski. Hello, Ariel, how are you?
Hello, I'm good. How are you, Frank?
Good. So, Ariel, you are a researcher at the SETI Institute. You work on the comets, cometary activity. You did a PhD at UCLA several years ago on this topic, right?
Yes.
And since then, you have been leading our citizen science at Unistellar SETI for cometary activity. So you know everything about comets, or most of it, right?
Yeah. Definitely.
Definitely. I love it. So, um, yeah, we have been doing this. We decided to do a SETI Live because there is a lot of news about this comet, about this interstellar visitor. And I think it will be great to start clearing the air and addressing some of the point of questions that we have been receiving over the past 2 months since this discovery. So, Ariel, is that a spacecraft?
No.
Okay, good. So let's go. Let's
Goodbye,
detail this.
everyone. Yeah. Yeah. Yeah, no, let's definitely take a deeper look into the why it's not a
Okay,
spacecraft.
we're gonna explain what we know about this exocomet and go through your questions as well. First of all, let us know where you're watching us from, and let's start. So this is very different. This is an interesting exocomet. It's the third one. So let's set the stage. What do we know about this? When was it discovered? And yeah, tell us a bit about the background story first.
Yeah, so this interstellar comet 3I Atlas was discovered on July 1st, so this summer. And it was very exciting because it was only the third one we've ever discovered. And it had been several years since the last discovery. We had 1I, Oumuamua, in 2017, and then 2I, Borisov, in 2019. And then we had a little bit of time before this third one was discovered. So it was kind of like, finally, a very exciting discovery, I would say. Yeah.
Yeah. So this was discovered by a telescope in Chile, if I remember, Atlas, right?
Yes.
That's the reason it's called 3I Atlas.
Yes.
And yeah, so let's talk about the comet. So a comet is made of a nucleus, there is a coma, there is tails, etc. So there was some kind of reports suggesting that 3I was kind of in the gigantic comet, up to 10 kilometer. Can you tell us what we now know about this comet, if we know about the size of it specifically?
Yeah, sure. So when this comet was first discovered, it was still pretty far away from the sun. It was approaching perihelion, so it's coming in to our solar system still. And at the time, the comet was around 17 to 18th magnitude, which it was kind of faint. For small telescopes, very faint. For large telescopes, it could see it just fine, but still on the fainter side and small on detectors. So when we have this image of this comet, it was kind of hard to distinguish it from the stars in the field. And the way we often distinguish comets from the stars and give it that cometary designation is by identifying that it has a coma. So you have, like you said, for comets, you have a nucleus. That nucleus has ices on it that eventually sublimate into gases. That gas carries dust with it and creates this coma around the nucleus, fuzzy cloud. And so it should look fuzzy in pictures. And so there was some debate around, is this fuzzier than the stars in the field or not at first? So there was assumptions saying, okay, let's just say all the flux that we're seeing, the brightness from what we're seeing is all coming from the nucleus, that there is no coma. At least maybe not yet, or maybe it won't ever have one, but for the no coma camp, if you take that brightness and give it an associated radius or diameter, you end up with something like 10 kilometers, something on the larger side. But very quickly, it was shown that this does indeed have a coma. So there was an astronomy telegram just a couple days later. So we knew right away that it had one. It was still a little bit debated, but we know it has a coma. So that changes how you measure the size of the nucleus.
So is it unusual that a comet that far has some kind of activity?
Yes and no. I'd lean no. Comets have a lot of volatiles on their surface, and that can be from water ice, which is what we expect. Kind of when we think of your classic comet, we expect when the water ice gets heated up, when it gets close enough to the sun, that then you start getting the coma. But there's also CO2 and CO, which is more volatile than water ice. And so that can start sublimating farther away at colder temperatures. And we see plenty of that in other comets too. So we've seen plenty of distant activity in comets before.
Okay. Before we continue this conversation, let me say hi to people watching us from Germany, from Bavaria specifically, from the Bayou in Louisiana, from New Zealand, from Sweden, from Mercer Island. I don't know where is that, and I will look. From New Jersey, this I know. West Virginia, Cyprus, North Carolina, Jacksonville, Brazil, and a lot of people from everywhere in the world. So we are talking about the Comet 3i with Ariel Graykowski, who is our Comet person at the SETI Institute. She's been working in this field for several years. Okay, so we addressed the size. So it may be probably a small comet, because when we started detecting it, we have the comet was already active, so he has this cocoon of dust and material around it that make it look bigger than
makes it look bigger than it is. And we've never just imaged the nucleus alone. And the comet is rather active, so that coma is contributing quite a bit of flux. So it is hard to measure the nucleus. There's estimates that puts it around a couple kilometers, a few kilometers wide.
Yeah. The good news is that when the comet will drift away from us, it will cool down. So then we will be able to derive the exact size of maybe get a better estimate of the size of the nucleus by then, if we observe it at when he has no activity, right?
Yeah, it would be definitely ideal to observe at no activity. Typically, when comets start leaving the sun, the activity kind of sticks around a bit for a little while, because that heat takes a while to penetrate the surface, and you have this kind of residual heating, and then you have kind of leftover stuff just hanging around. But yeah, hopefully we can follow it to a point where we can get a much better estimate of its nucleus.
Okay, so when we observe a body like this, we take pictures. So we have an idea of the size, if we can, from the brightness, for instance. But we can also take what we call a spectrum. So in this case, we split the light and we look at what absorption band we can see, so we can get some idea of the composition of the comet. So there was some report that this comet was rich in carbon dioxide, but very poor in water. So what does that mean? And is that common for comet?
Yeah, so this report came from a paper using the spacecraft SphereX, and they were taking a look at the water coma versus the CO2 coma, and they noticed that the CO2 coma was very dominant, and there really wasn't much of a water coma at all. So this means they didn't see a lot of water in gas form, but they did detect that water was present, which indicates that probably in chunks that were coming off of the nucleus, there was water ice that wasn't sublimating, which is a little weird, because at this point of where it was in the solar system at the time, it was close to 3 AU. We expect around there that water should start sublimating. The idea was maybe that since there was so much CO2 sublimating, which does sublimate before water, it caused a sort of evaporative cooling. So maybe the local temperatures were colder, than what you might expect without all of the CO2 sublimating off, kind of suppressing that water sublimation. So water was present, it just wasn't in the coma at the time, which was a little weird, but not crazy.
Not crazy.
Yeah.
Um,
Kind of interesting for sure.
Is that coming? So it's coming from a difference of composition as well, or can we also consider that this could be the case?
You definitely can consider this could be the case. I mean, this comet is coming from a whole different system where it was formed under conditions that we don't know. We study our own comets to try to understand our own starting conditions in our solar system, and we still have a lot of questions about that, even though we have all of this evidence. We live in our solar system, you know, we can see a lot of things, we could go a lot of places, but we can't to this system. So it could be indicative of its composition. It also could be indicative of the fact that it was coming in so fast. This comet was coming in faster than the last two interstellar comets. And it could basically be a tell to basically that heat penetrating far enough to cause the sublimation. There's this delay, like I mentioned earlier, because the dust and everything can kind of insulate the comet a little bit. And it takes a little time for the heat to penetrate. And because it's going so fast, then when normally we would expect at this point for the sublimation to start, maybe that delay just seems longer because of its speed. So I've seen that idea thrown around too. So it could be different physical explanations.
Yeah. I've also seen, like, this is a study that was conducted at UC Berkeley by a group of chemists, that if you have ice in the interplanetary space, basically, for a long period of time, this is not going to be the same ice that you have in our solar system, when there is still some residual of heat coming from the sun, plus you protect it from the bombardment of cosmics. So the ice in this interplanetary system, when you can imagine that this body stays over there for like millions of years, may be different in terms of the structure, the crystalline structure, but as well the type of material embedded into the ice. So when it comes to, for the first time, close to the heat, our sun, it will behave differently. And that's maybe the reason we see this kind of weird emission of ratio of CO2 versus water and others. That's not impossible that can be explained by simply the nature and the origin and the history of the comet itself.
Yeah, and I think that's what makes it so complicated and therefore so interesting, because it could be a compositional thing. That compositional thing could be related to its origin in its system or its history moving through space for millions of years, you know. So it's always some combination of all these things usually. But what is the composition? We have to kind of untangle that.
Let me say hi to a lot of people who join us. We have Maine, we have Greece, we have people from Staten Island, Mexico, Germany, Switzerland, India, and I think the world is very interested in this comet. Belgium, they're talking about chocolate. I don't know why. St. Petersburg, Florida. Okay, and Idaho. So welcome. We're talking about the the exocomet 3I Atlas. So we talk about the coma. Let's talk about the orbit, because that's a very interesting point. So this comet has an orbit that make it basically behind the sun. That's the reason we cannot observe it now. There is very few spacecraft that can observe it, because right now it's passing behind the sun with respect to us. Some people claim that it's a design from extraterrestrial civilizations. But seriously, is that uncommon to have comets passing behind the sun?
It's very common. So basically what's going on this past month, around a month, we haven't been able to observe the comet from Earth because it is behind the sun. That is where its orbit has taken it. With comets in our solar system, I'm talking about like long period comets in particular that come from the Kuiper belt and Oort cloud. They come close to the sun when they get perturbed from their source region. They get on a new orbit. That orbit is highly elliptical, and it takes them very close to the sun during perihelion. And oftentimes that comet goes behind the sun or between us and the sun, and there's a period of time where we can't observe it because it's too close to the sun. We'd be looking at it during the day, which we can't do. This happens quite a lot, especially comets on an extreme orbit coming close to our sun. So it's not an evasive maneuver. It's
not an evasive maneuver. What a disappointment. Disappointment is this. Okay, so.
Well, I wanted to just highlight another kind of example of this happening recently. Comet R2 Swan.
I was about to say that. Thank you.
Yeah, we only discovered it after perihelion. Before perihelion, it was probably too faint. It just kind of evaded discovery. And then there was a period where it was too close to the sun. And then when its orbit took it to a spot where geometrically from Earth we could see it, it was really bright. So maybe it went through some kind of surge. It's hard to say what happened to it since we didn't discover it till after. But this is a very natural object, and this happens all the time. It happens with asteroids too.
And Swan is a comet that now is passing nearby us. And if you have a telescope, like a unistellar telescope, you can watch it by yourself, and you will see that it's a comet with a coma and a tail and behaving like a normal comet.
Yeah.
Okay.
And it's pretty. So take a look.
It's pretty. Yeah, we have pictures. I don't know. If you look online, you will see a lot of pictures. Go to our SETI website. I think we posted one recently on our social media. If not, we will. So we have the orbit passing behind the sun, and then there is also some small changes reported in the orbit that is not basically following a purely Keplerian orbit. Can you explain this to the people so they understand what we're looking at exactly here?
Right. So comets can be affected by non-gravitational acceleration. This is a force that's applied to a comet or a body that doesn't have to do with the gravity of the sun pulling it around its orbit, right? And so if you have a force placed on you, that'll kind of push you out of your trajectory a little bit onto a new one. This can happen in comets ever so slightly because of their activity. They're losing mass. If you throw a ball, you can feel the force on your body when you throw it, right? So it's those kind of forces that can affect a comet's trajectory, usually a bit, but for that reason, it's important to keep track of comets because their orbits can change a little bit. We need to make sure that over a long period of time, we know where they are. But yeah, this can happen in comets. This is a common thing.
Okay, so this is what we call non-gravitational effects.
Yeah,
basically, and people can imagine like you have a kind of a potato-shaped nucleus, and this basically has some kind of very volatile element, and then there is vaporization, some explosion, and emission of gas and dust, and basically because of the Newton law, this is pushing away the nucleus as well. That's what we're observing here. It's basically action-reaction due to the fact that we have emission of gas and dust, so it's slightly modification of the orbit. We have seen that for comets, I'm assuming, in the past?
Yes, we have.
It's very common.
Very common, because if you have an area that's releasing a lot of mass, you're going to apply a force, a torque or a push of some kind.
Okay. And so what astronomers do is that they monitor the orbit of comets. So we have been doing this with the Unistellar Network. Maybe you can explain what is Unistellar and what we do. I mean, I have a Unistellar telescope in the back for those who really did not look at any of our SETI live in the past. This is a Unistellar telescope. It's a small telescope you can carry around and buy anywhere you want. So what do we do with the Unistellar Network for this comet?
For monitoring a comet, the way we want to monitor 3I, the Unistellar Network is an extremely great tool. Basically, if you have one of these telescopes, you can participate by taking data and uploading it, and we compile results all together. And we look at how the brightness changes over time. We monitor when outburst happens or a surge in brightness happens, we're able to do that very easily because the network is big and it's all around the world. So it's nighttime for someone somewhere on Earth that we can continue to monitor this thing. And we can basically compare its position on the sky to the stars in the field in order to know where it is and keep track of that every day. Yeah, make sure the orbit stays up to date.
So shortly before the comet went too close to the sun to be observable, we noticed something interesting with the Unistellar Network, right?
Yes.
Can you explain what was this brightening?
Of course. So it was pretty shortly before we couldn't observe it anymore. The comet started brightening. You're probably thinking, yeah, it's getting closer to the sun. It's brightening. That's what you said happens, right? Well, it was brightening more than expected. So we had been monitoring it for a while. We were modeling its light curve, we call it, so we could see how bright it was going to be in the future. We could see kind of the rate at which it was brightening. And then suddenly that rate of brightening increased. And at first it was just a little bit, and we weren't sure. There was a lot of discussion in the field, like, is it or is it not? Are people using different aperture sizes and getting different results because of that? But we were able to confirm that even using a consistent measuring technique, that this brightening was happening, and then it went behind the sun. So we were very curious what this was. Was this an outburst, this fragmentation event? What is causing this surge? Is the surge continuing? How long will it continue? Will it make the comet fizzle out? We've been kind of waiting to figure out what's going on till it comes back. But
go ahead. But last night we saw something. Go ahead.
Yeah, there's been a recent report using that people have been using spacecraft that image very close to the sun or image the sun. So they have this ability, unlike our ability on Earth. We can't look at the comet right now. These spacecraft can. So they've been monitoring it, and this surge in brightness has continued. So that rate that we were seeing at first is continuing. Now it recently hit perihelion on October 29th. Around now, like early November is when you can start observing it again from Earth. So I'm really curious to see how much longer this brightening is going to occur, or if it's going to come down now, to try to figure out why this happened. But I think people have a pretty reasonable idea of why.
Yeah. So if you look at this data, this was published last night.
I think a couple of days ago, maybe a few days ago.
Okay.
Yeah.
Well, I saw it last night. Sorry. So you can see the brightening, and you can see the profile, and there is a few points because there is very few spacecraft that can observe so close to the sun or behind the sun. In fact, there is very few of them because we generally have the telescope. Most of the telescopes are on Earth or orbiting around Earth. So this is a very cool result. And I really thought I posted that yesterday. I think it's a remarkable how the community of astronomers have all been working on with all the available instruments to observe this comet using telescopes or instruments that were not dedicated to observe comets. They basically pointed toward this area of the sky to see this comet and to detect it so close to the sun. So that's one of the reasons people have been criticizing the quality of the data. People need to understand that when you point a camera which is supposed to observe the sun to an area to search for a tiny dot, which is a comet, of course you're going to have an image which is very poor in quality and or very small, because it's a wide field of view instrument that you are using to detect a tiny dot nearby. And generally, the tiny dot is so close to the sun that you can even see the light coming from the sun. So there's some answering to questions that we're already getting about the quality of the data, because people need to understand that when you observe close to the sun or behind the sun with instruments like this, they're not designed for that. They have been designed to observe the entire sun or the corona or whatever you interests you in the sun, not to observe comets.
Yeah, so that definitely provides an extra challenge. But this paper that did come out does show some data that I think their data looks pretty nice actually compared to
Yeah.
some of the other data I've seen. So it's definitely worth taking a look. There are pictures. If you're skeptical, they exist.
And this is available online, and you
Yeah.
should have a look if you want to check by yourself. I mean, this is the way science works. It's not on social media. You're gonna find this paper. You can find a link to the paper on the figure maybe, but that's all. If you want to really see something like an image, take a set of images, have a look at the paper directly. Okay,
Yeah.
we have another point of discussion, and I know there's a lot of questions popping up. So thank you very much, guys, for listening to us and watching us and providing questions. I'm trying to drive the conversation so we answer to some of them in real time. Let's talk about the nickel to iron surprise. There was some observation with the VLT, the Very
Yeah.
Large Telescope of ISO, that shows some unusual high nickel to iron ratio. So what's that? Why is that such a big deal?
Yeah. So basically, they've released data from several epochs of this comet's orbit. So as it's getting closer to the sun, they've reported this nickel to iron ratio, and it's been changing. But basically, at first, this nickel iron ratio was very, very high. Basically, we're seeing nickel, but we're not seeing iron. And that's a little bit weird because we expect to see iron when we see nickel in our own solar system. But as this comet is getting hotter, is closer to perihelion, that ratio is changing. It's still high, I believe, but it is getting lower. So the iron is showing up. And I think it's weird. In general, we start to ask this question, why are we seeing this in comets that seem to be too cold to be sublimating rocks or metals? Why are we seeing metals in the coma? That seems strange. It makes you think, oh, it's a special metal, must be alien spaceship. But actually, we do see this in other comets too. We see this nickel and iron. The nickel to iron ratio in other comets is higher typically than what they have found for 3I, but we do see it. And there's theories about how this could happen. And it's this idea that there's a parent body of this iron and nickel that can sublimate at very low temperatures. It's this kind of organometallic carbonyl, something like that, where it's attached to carbon. And then that breaks down very quickly when it sublimates, and then you see the iron and the nickel. So it was a little strange that we saw so little nickel early on. But the fact that we are seeing nickel and iron is good for this hypothesis about these organic metallic materials, which has still been a theory about our own solar system comets.
And we have seen variation of nickel iron in the past on other comets, right? I remember I read about this very weird comet that was coming from our own solar system, but has also a very different ratio at the beginning.
Yeah, and so the fact that the ratio is changing too is really telling, that the iron is there and is coming later. I think if it continues changing at the rate that it's changing, the paper estimated that eventually it's going to look just like our comets in that regard. So it tells us something about maybe, again, how the comet formed. What did it have available to it in its solar system when it formed? How was it affected in space? Or is it some heat delay because it's moving too fast in our solar system? Kind of similar reasonings that we talked about before, causing this iron delay sort of thing. Yeah. And
this is the paper which was published, and the data are available as well, if I remember correct.
Yeah, everything we're talking about, their papers are published, and they're all at least accessible on arXiv. If you guys want to take a look, they're very searchable.
Yeah, and I'm seeing a lot of conversation about government hiding, etc. So I just remind you that we are a non-profit organization, and we are not the government. So first of all, and data that we are talking about are open access for most of them. If not, you can
Yeah,
ask the first author of the paper, he will send it to you. And the
definitely.
papers are also accessible to everybody on the archive. The only difference here compared to a blog post is that the paper that that published by our colleagues are peer reviewed, meaning that some other scientists can basically ask for correction or challenge some of the results, but that's all. It's not a blog that someone can write in his office by himself alone and make up crazy stories. Here we're talking about papers which have been published together with a group of scientists who are not government. Scientists are people like you and me, and we publish paper, but we're cautious of what we say. And we have been studying this field of comet activity for years in the case of Ariel and other people. Okay, let's continue this. The brightening and the turning bluer. This is something new. I think yesterday I get a lot of questions about this. So
Yeah,
3i Atlas is brightening and its color is shifting toward the blue. So
right.
what does that mean?
So not only is it getting the surge of brightening is continuing through its perihelion, its color is now very blue. It's bluer than the sun, which is not very typical of comets. We tend to see things in our solar system look redder than the sun, as far as when we look at these things in very standard filters, and we look at the difference between those filters. That's what we mean by color. Basically, what we think is happening, because at first this comet was rather red, and it was said to have a very, very dusty coma, and dust reflects red wavelengths very easily. So if you get a really red object, especially a comet, you can pretty much say like, oh, that's a dusty comet. If it starts getting bluer, that means we're starting to see more gas within that coma. And so this is kind of an extreme change that has been seen, but it seems like its gas has really taken off. The sublimation is really going at it during perihelion time, and now gas is dominating the coma, whereas dust dominated it before. So the gas particles are smaller, and they tend to peak in bluer wavelengths, green to bluer wavelengths. Yeah.
Yeah, that's a very good point here because someone is mentioning that color is temperature. No, color is not only temperature. Color is also the size of the grains, is also
Yes.
the composition of the gas. I mean, there is a lot of very colorful things in space which does not depend of temperature. Look at me.
Yeah, when we're
I
talking
have the same
about
temperature, but I have a different color, right? So
yeah,
that
that's a good
explains.
point.
Okay.
Yeah, when we're talking about colors of solar system bodies and planetary bodies in our solar system, we are talking about basically it's a proxy for what we're seeing compositionally on its surface, or whatever light is being reflected. That's what we're seeing. We're not measuring the temperature with that at all. And I think this is really important because this has been the latest finding, and this is the latest kind of hubbub around this finding, is that, oh, it must have a power source hotter than the sun. But that is just very wrong. It has nothing to do with temperature.
Exactly.
Yeah.
Okay. I think we went through a lot of different points. Did I forget anything, Ariel? Because I know we prepared
Oh,
this. It was a long list of questions and ideas.
yeah, there's been a lot of things. I'm sure we forgot some little things here
All
and
right.
there,
Let me
but
look at the questions from
yeah.
people. All right. There's a lot. Sorry. Uh-huh. Sorry, I'm reading. There is a lot of questions we already addressed. Do we know the age of this comet? That's from Tony Mac.
There are estimates based on the orbit where we think it came from. It seems to be old. I don't remember the age. I don't know if you do, Frank.
How can we find the age of something which is coming from another planetary system? Do
Yeah,
we
I
do
think
color? Go ahead.
from what I've seen, it's just been estimates of its orbit and how long it must have been in space and which system it came from, and therefore how long it's been in space before it hit us. And this is just through backwards modeling of its orbit.
Okay. So we had a lot of questions about the image quality and the fact that people see pretty pictures coming from Hubble Space Telescope of galaxy which are so far away, and we don't see pretty picture of this comet. Can you tell us a bit more about that? Why we don't have a picture where we can see all the jets and the nucleus, etc., of this comet?
Yeah, I mean, what we can see is just what light is being either emitted or reflected, and so we can see a lot of galaxies that are bright, even though they're far away. They're bright. They're sending us a lot of flux, um, and this one is sending us just the flux that it's sending us. It's not huge, and we're not particularly close to it either. This is a small thing, so it's hard to resolve features that are smaller than our pixels on our detector.
Exactly. Because the quality of a picture does not depend only on the size of the telescope. It depends also of the field, also from the field of view, the wavelength, and what you have nearby the object. Okay, so that's the reason we have sometimes a fuzzy blob, and you see a picture with a few pixels, because in fact it's a cut off of a bigger picture, and we just send you the tiny picture. We can see the comet.
Mm-hmm.
The apparent magnitude estimated now is 8, right? Based on
I
the
think
recent
so.
observations. Yeah.
Yeah.
So, what's going to happen in the future? It's going to increase, decrease if it behaves like a normal comet.
Well, so it's past perihelion, so I'm expecting it to start decreasing in brightness.
Yeah. So
Unless,
perihelion means the closest point to the sun
yeah.
in the orbit. So for people so it means that you will receive less energy from the sun,
Mm-hmm.
and reflect less light from the sun. So it should be
Yeah.
decreasing in activity.
Yeah, as it moves
Um,
away. So
yeah.
unless
When
it
it's
has like an actual outburst or something, which could be possible because seems to be a lot of volatiles, there could be something strange that happens. But I wouldn't say I'm expecting it. I think if this were just to keep sublimating the way it is now, it's moving away from the sun. There's less energy now.
So we have we know that NASA JUICE mission is going to try to observe it as well, right?
Yeah, I know there's plans to try to get that to work.
So
I
it's
think
a
that'll be,
mission. Can you
yeah.
explain the mission? What the JUICE is?
JUICE is a Jupiter orbiter. And so there will be a time, I believe in the spring of 2026, where there's going to be it's going to be close enough to this spacecraft where the spacecraft will be able to image it.
Yeah.
So hopefully we
And
can just
Clipper.
continue. Oh,
Yeah.
and Clipper,
Clipper
yeah.
will also try to observe it, another spacecraft.
Yeah.
So we are lucky because we're living in the time where human beings been sending enough spacecraft to different planets that we have now some of them en route to Jupiter. And on the way to Jupiter, once again, they will basically modify the software on board and take observation of this comet. I'm not fully aware of the plan for Clipper, but for JUICE is going to be very soon. In fact, it's going to be this year. And the
Oh, JUICE is
advantage
this
of
year.
this observation is that they may be able to observe at different colors and wavelength, not only in visible like we had right now, but there may be also some UV and some infrared as well. So when you observe in the broader wavelength range like this, you can better differentiate what's coming from the size of the grain, what's coming from the temperature, and what's coming from the composition. And that's the reason it's very important to have a broader wavelength. Unfortunately, from the ground, you cannot observe in UV, and most of the infrared is also not accessible. So we have to have spacecraft in space to be able to do that kind of observations.
Yeah.
Okay, anything? Well, go ahead. While I'm looking at the other questions. If
Oh.
you have any.
Um, yeah, I think I was just going to add that like this is a really exciting object for everybody. So if there's any spacecraft in space that has a chance to observe it and has some kind of camera or spectrograph or something, scientists, we all want to turn our eyes and look at it for as long as we can. The longer we observe it, the better, the more data we have, the better, right? When it was behind the sun, it was really kind of sad when we thought we didn't have data, but actually we do have data to fill in that gap of time, and it tells us a lot. It tells us that gas has really turned on, for example, which we wouldn't have understood as well if we didn't have that. So as much data for as long as we can is very important to understand the physical aspects of this comet.
Yeah, because in the case of Oumuamua, we discovered Oumuamua while he was leaving. So we missed basically the activity. We missed the most interesting part of the activity of this comet.
We didn't get a lot of data just overall with Oumuamua, which was really sad because it was our first one. So it was like, oh, give us more.
Okay, so we are going to see more of those interstellar comets, right?
Definitely.
Can you tell us a bit the background of what's happening in the future?
Yeah, so there's a new telescope that recently had its first light, the LSST or Vera Rubin telescope. And this is going to be a survey telescope, and it's going to really catch a lot of these small bodies for us. It's going to scan the skies every night, and I think it's going to really increase the number of things we find in general. It's going to increase the number of our own solar system comets that we discover, asteroids, and also interstellar objects. So I think a time is coming where we're going to start having a lot more data than we have now.
Okay. And there is this mission. Do you know anything about it? It's called, let me check again because every time I forgot the exact name. Comet Interceptor. You remember that mission?
Yeah, I do remember that mission, but I don't know like their plans on launch or anything.
Launch 2029 with an Ariel 6. It's an ESA mission. All right. So the point of this, it's going to be a mission that we're going to let float in orbit. I think it's going to stay in the L1, Lagrange-point of the Earth sun system, something like that. And it's going to wait for us to find a very interesting comet, an interstellar comet or a pristine comet. A pristine comet means that the comet which probably come for the first time in the inner part of the solar system, right?
Mm-hmm.
And when we discover one of those, we're going to launch this spacecraft. But we're going to send this spacecraft because it will be already launched. It will be in space waiting. So we're going to send it toward the interstellar comet. And this way, we will have in situ observations of the comet, be able to see the comet, see the nucleus, and see the activity and follow it over a long period of time. Yeah,
and maybe even fly through its tail and collect some grains and see how big the grains are, how icy they are. But yeah, this kind of laying in wait approach is really important for a comet mission, especially because we don't want to just go to any comet. We want to go to one of these very interesting ones that is potentially going to be interstellar or a dynamically new comet. We want to be ready. And that's kind of another thing about this one. I do see questions. I've just heard questions. Why aren't we sending something to this one? It's just not so simple. We can't just build something and send it and catch up to it quickly enough. So it's important to have something ready to go for the next time we discover one of these things.
Yeah. And one of the reasons, for instance, we also have the IAWN, I think they call it I1, program activated. It's also to train scientists on the idea, on the opportunity of us seeing a comet in the future and be able to send a spacecraft. Because if you want to send a spacecraft like this one, very close to the comet, you need to have a very precise estimate of the orbit of the comet. So they activated the I1 program now for this 3i Atlas. So we train scientists, we acquire data, we put them together, we derive orbits, and we have a very accurate estimate of the orbit of the comet, taking into account non-gravitational effects, for instance. So we will be in the future capable of sending a spacecraft. So this is a kind of a training session. That's the way I understood from the press release and from the conversation with my colleagues. Do you know anything more about that?
Yeah, that's the way I understood it too. And I think it's a really good opportunity to teach the community, teach anybody who wants to learn how to do astrometry on a comet to do it, because a lot of people are observing from their backyards with unistellar telescopes, with their own telescopes, and they want to be able to take that data and contribute to pinpointing where it is and refining that orbit. And for comets in general, this just is a challenge because of that coma. So figuring out where that center is, where that nucleus is, where most of that light is coming from, pinpointing that, it can be tricky. And then comparing that to where the stars are in the field. So I think this is a really good opportunity to kind of sit down and go over it with the community, teach the community, train a lot of people, because a lot of people want to learn this right now. I think it's great. And we want to keep track of where 3i is going too, of course, just like we want to keep track of every comet so we don't lose it until we do, of course.
So this one is not coming back, right?
It's not coming back. It's on its way out, and maybe it'll go to another system.
Maybe you come to another system, and those extraterrestrial species over there will be writing on blog posts and scientific paper, hopefully, more than blog posts, explaining and trying to understand the origin of this exocomet. And maybe we think we send it to them.
I thought I was going to say, they're going to be able to tell it came from our system first. They're going to say, we hopped onto it. It was easy for us to hop on, and we're coming.
All right. Thank you very much, Ariel. That was a very nice conversation. I hope everybody here watching us, the thousands of people watching us, learn and discover a bit more about how scientists study comets and exocomets, and why this one is extremely exciting. It's not a spacecraft. I mean, I would love it to be a spacecraft, to be very honest with you. Everybody at the SETI Institute, we love that.
We're very incentivized to say it's aliens. But
but Rana is not. It's a comet unusual. There is some very interesting things happening because it's coming from another part, another planetary system, and we are learning together. All of us are learning how to observe this comet, how to analyze the light of this comet, how to interpret data, and so on. And you will see mistakes published. You will see maybe crazy theory published, but at the end, we probably will sit together and say, well, that was a very interesting exocomet. Let's get ready for the next one. And we will.
We will.
Okay. Thank you again. And that was the SETI Institute SETI Live, the third one of this week. I hope we not bore you too much with those SETI Live this week, but this was kind of a great timing, we believe, to have a conversation about 3i Atlas. If you like this show, don't forget to visit our website, seti.org. You can make a small donation. There is a link, donate or something like this, to support the research and specifically this program. You can also like this video. We are streamed on every social media platform. We scientists that who likes to talk to people and talk about the beauty of the solar system and the search for life on other planets. So if you have any questions, comments, if you like something, dislike something, if you want us to clarify a few points, just write down the questions at the bottom of this video, and we will take the time to answer to you. And maybe have another show where we address all you remaining questions. Ariel said that she wants to come back, right?
Of course.
Okay, good.
Always.
Thank you very much, Ariel. Thank you to the team, Beth, Rebecca, and everybody else in the background here that make this show and make this last-minute opportunity possible. Thank you, and see you soon.
Happy Halloween.
Bye-bye. Happy Halloween.